just look at a couple of examples of finding dimension for various subspaces, and we'll try and get a look at some different ways we can describe subspaces as well. So for this first example, we'll go ahead and take W equal to the set of all x's, such that x is an element of R3. And we've got some specific requirements. x1 is going to be equal to minus 2x3, and x2 is equal to x3, and x3 will be an independent or free variable. So here's our subset W. In order to figure out the dimension of this particular subspace, we are going to first describe it, and then we'll write it in vector form. Once we know how many vectors are in the vector form, then we can determine its dimension. So the vector x, any vector in this space, again comes out of R3, x1, x2, x3. And applying the specific conditions for x1, x2, and x3, we have minus 2x3, x3, and x3 for each of those. And just writing it in its vector form, which we should be getting pretty familiar with, minus 2, 1, 1. And we see now that any vector x that's in this subspace W has to be a multiple of this one specific vector. So that means the dimension is equal to 1. And if we wanted to describe this geometrically, this would be a line passing through the origin in R3. And that's just coming from the idea that if you write this out as a parametric equation, we would get the parametric equation for that kind of a line. So let's take a look at another example. And here we'll describe W in a slightly different way. So here we'll have x1 plus x3 minus 2x4 equals 0. And then we'll have another line that says x2 plus 2x3 minus 3x4 equals 0. And it's the same kind of story. We need to describe all the vectors x in this set in terms of some vectors, and the number of linearly independent vectors. The basis for that set will then ultimately tell us what the dimension is for that particular set. So let's go ahead and write these out. Now in the first row here, x1 is going to be equal to minus x3 plus 2x4. And for the second row, x2 is going to be equal to minus 2x3 plus 3x4. And although x3 and x4 aren't listed as part of our set, they certainly exist. x3 is independent, and x4 is also independent. So now I've got a description for all the vectors x in our set. It looks like they're coming out of R4. And we would then go ahead and write this out in their vectored form. So this would look like x3 times minus 1, minus 2, 1, 0, plus x4 times 2, 3, 0, 1. And we see we have two linearly independent vectors that span this particular subspace, so the dimension here is equal to 2. And although we're in R4, I guess we've got a couple of vectors here, so this would form, from a geometric standpoint, some kind of a plane. And let's take one more example here. Where we look at a particular set of vectors. And just for a little bit of review, we should be able to ask ourselves whether or not this set serves as a basis for all of R3, and we would answer no. It's got 4 vectors in R3, so we know that this is not a basis. Again, a basis being the minimum spanning set. So the fact that we have 4 vectors in R3 tells us this is not a minimum set, and we would have linear dependence here for sure. So just a little bit of review on that. So now again, what we want to do is, in this one, determine the dimension of the subspace W that's spanned by this set. So that means we're going to have to determine a basis for this subspace W, for the spanning set, which is really the same thing as asking for the range of the matrix or the range of the column space formed by these vectors if we were to throw them into a matrix. So that's what we do. We'll take all these vectors and put them into a matrix. So 1, 1, 2, 2, 4, 0, 3, 5, 2, 2, 5, negative 1. And again, what we're after here is to turn this into a basis. And we can do that using processes that we've already been through. In this case, we're really just concerned with the dimension of the subspace. We don't need the actual vectors, although we have a process for figuring out exactly what the basis vectors would be from this, using a transpose and some row refing and transposing back. In this case, if we just RREF here, so if we row ref this, what we would get is something that looks like 1, 0, 0, 0, 1, 0, 1, 1, 0, and minus 1, 3 halves, and 0. And if we just remember that the dimension of the row space is equal to the dimension of the column space, we can quickly identify I've got 2 non-zero rows. Not that this represents any kind of a basis for our column space, but it tells us how many vectors would be in that column space as far as the basis is concerned. So the dimension here would be equal to 2. Again, I don't have the specific vectors that make up that basis, but I do know that I need 2 vectors to do that. The other thing we can kind of key in on here, if we want, is just note that I have 2 leading 1s, and this column doesn't have a leading 1, and this column doesn't have a leading 1. So we would know then again that the dimension would have to be 2 based on these the location of these 2 leading 1s. So again, now we can get the dimension of the span of those vectors. Again, the span of the vectors being the same thing as the dimension of the column space of this matrix when we throw them all in there.